This call is now being recorded.
Okay. So last time we spoke about modeling and the various types of models, and we said a little bit more about mathematical modeling because that is what most scientists do. And in mathematical modeling, we said there is a modeling cycle where you start by framing the problem, then you mathematize it, and then you finally use it to get outcomes, and then you validate the outcomes. Okay. Now, this is the basic structure of any mathematical model, but we need to go into a little bit more detail before we can actually attack a problem with a mathematical model. So what are the ingredients of a mathematical model? So this is something you know again. So this course is more or less everything you know, but put into a formal perspective so that you realize the interrelationships and how everything is organized. So in a mathematical model, you will obviously have variables and parameters. Now, what is a variable? And how do you distinguish a variable from a parameter? So the variables are the inputs to a function whose effect we wish to see directly. So when you write something as a function of x and y, then x and y are the variables. Simple enough. Now the two variables, they may be either independent or dependent. So you've encountered this when you have done partial derivatives, for example. So x and y may be two independent variables, in which case dy dx is 0. But y may also be a function of x, in which case they are dependent variables. Okay. And then in addition to x and y, you may have some parameters. So they are supporting inputs for a function. So your function may be mx plus c, for example, the equation y equal to mx plus c, the equation for a straight line, in which case m is the parameter. So it is the slope of the line, as you know. And for a fixed value of m, you can plot y as a function of x. Again, if you change the value of m, you can plot another line, etc. So these are parameters. So these are the inputs to the function which remain constant while solving for the variables. And these parameters may be adjustable or non-adjustable. So an adjustable parameter is something like the slope m. So if you have y equal to mx plus c, for example, m is a parameter. And this is an adjustable parameter. C is also a parameter, if you like. But you can also have something, a formula, say S is equal to ut plus half or minus half gt squared. I don't like this scrolling. Okay. In which case, G is a I don't know how to write it without touching that. Okay. So G is also parameter, but it is a non-adjustable parameter. So it is a true constant, so to speak. So it is a constant parameter, which you cannot change. But then this is, of course, again, context dependent. So if you're plotting S for the Earth and the Moon, then G is an adjustable parameter. So it depends on your model. If something is an adjustable parameter or a non-adjustable parameter. Okay. And among these variables, you have some fundamental quantities. So some properties of matter which have been decided to be fundamental. And these are mass, length, time, temperature, and charge. So this is sort of from the point of view of dimensions. So these are unique dimensions which are independent and cannot be derived from each other. So we have 5 of them: mass, length, time, temperature, and charge. All other quantities or variables that occur in your model, they are derived quantities. These may be, for example, things like velocity, force, pressure. You can think of other things, density. Okay, these are derived quantities which can be expressed in terms of fundamental quantities. And using the fundamental quantities, we can do what is called dimensional analysis. So this is one of the simplest ways of figuring out the relationships between the variables and parameters in your model. So when you have a model, a mathematical of a problem, then the first thing, once you have identified the question that you are asking the model, you need to find out the variables in that model. So what are the inputs to this model? What is the output that you want? Okay, what information do you have? Do you have any information about the relationships between some subsets of variables or among all the variables? So once you have looked at all of this, then the final step would be to know how all the variables depend on each other. Okay. So usually, and that is basically finding out the formula from your, finding out a formula from your model, let's say. Okay. And the simplest way of doing this is dimensional analysis. You have all probably heard of it. I remember the first time I did it was during my 11th standard, I think, in physics. So is there anyone who has not done physics at the +2 level in this class? No? Okay, then it's fine. So then all of you have done dimensional analysis, at least the basics of it, okay? But we will go a little bit beyond the basics in this class, hopefully. So what is the principle of dimensional analysis? The principle is that an equation must be dimensionally homogeneous, which means that the dimension of the left-hand side must be equal to the dimension of the right-hand side. And in this equation, you must consider dimensions not only of the variables, but also of the parameters. Okay? Or if you have some constants, the constants may be either dimensionless, in which case they don't matter, but they may be constants with dimensions, which in that case you must know the dimensions of the constants as well. Okay? Now, usually, the dimensional analysis is restricted in its scope. It's not like you can find an equation for a model by dimensional analysis in all cases. Okay, it's a bit specialized, but when it works, it's usually the simplest method of arriving at that formula. The most common applications of dimensional analysis is to find the dimensions of a constant. So when you do an experiment, usually you find how one variable changes with another. So usually your output from any experiment or study is a plot of something versus something. You change one variable and you see how the other one changes. Now, if this is a straight line or something, then you straight away know how this, let's say, y depends on x. But if it's a complicated plot, then one way of finding out how y depends on x would be to fit various functions to it. That is an alternative to dimensional analysis. For example, that you fit the plot to get the function. But then this would normally be for pairs of variables. If you have have a relationship between 4 or 5 variables, then fitting functions is no mean feat. So it is not something that you can do. In which case, again, dimensional analysis might be the way to go. And okay, so that's how I saw it. Sorry, I was talking about finding out the dimensions of a constant. So now let's say you have a plot, okay, and you know how y depends on x. You know that y depends on x, but you don't know how it depends on x. And then let's say by fitting you figure out that it depends on x squared. And then you would have some proportionality constant here then, if you want an equation, which is c, let's say. But what is the significance of c? So if you do a dimensional analysis of y equal to cx squared in that case, you can find out the dimensions of c. And often, this dimension of c gives you an intrinsic property of the system that you're studying. So this is some sort of constant for your model, definitely, and which means it's a property of the model. So most commonly, if for example, if you see the simplest one, F is equal to ma. So if you do an experiment and you study the force with the acceleration, then the constant of proportionality m, the dimension of it is of course mass, and it will tell you that mass is the property of the system which contributes to the force that it exerts when it's moving. Okay. So that is the sort of a direct application of dimensional analysis, which you can always do. Then check the correctness of the equation. This is also something you can always do. So if you have derived an equation, you can match the dimensions of the left and right, and most certainly they have to match. If they don't match, your derivation is wrong. So this is also doable all the time. Now the third one, which is to derive the relationship among the variables and parameters, which would actually be the most useful purpose. This is not such a universal thing. You can't always do it, but we will see when we can do it. And there are two methods to do this, the Rayleigh method and the Buckingham Spy method, which we will learn today. But before that, just 2 more points. I know you know this, of course, that only quantities of the same dimension can be added or subtracted, and ratios of similar quantities are dimensionless. It's pretty obvious. Now let's look at the methods for dimensional analysis. So there's the Rayleigh method. So the Rayleigh method is what we are taught in school about how to find out the relationship. So we'll take an example here. So we know that, so from an experiment, we have figured out that the time period t of a pendulum depends on length of the string L and acceleration due to gravity G. So T is a function of L and G. What we don't know is the functional form. So we assume that the time period is, okay, let me write the proportionality first. So the time period is proportional to some power of L and some power of G. Okay. And as you know, to convert it to an equation, we need a constant of proportionality, K, L to the power A and G to the power D. Okay. Now let's look at the dimensions of the left hand side. So in the left-hand side, we have time period. So we have time, then we have a constant, then we have the dimension of length to the power a, and then acceleration due to gravity is acceleration, so length per time square to the power b. Now let's match the powers on either side. So L has the power of a plus b. So a plus b equal to 0. There is no length on the left. And we have the equation for time, which is minus 2b equal to 1, which means b equal to minus half. And I put this in this equation. So a is equal to minus b is equal to plus half. Therefore, we easily find the relationship T is equal to K square root of L by G. Okay. And from your usual physics knowledge, you know that K is equal to 1 by 2 pi. But this comes from, what should I say, external knowledge. So dimensional analysis would give you root of L by G, but it would not give you the value of K. So this is the simple Rayleigh method. Now let's talk about the limitation of the Rayleigh method. Okay. So let's try a more complicated example. So we say that the resistance force of a moving object depends on its, so let's see, resistive, I have enough space, so resistive force of a flying object R is a function of the length of the object, the velocity of the object, air viscosity mu, air density rho, and the bulk modulus of A, kappa. Okay. So let me write what all these things are. This is length of the object. This is velocity of the object. This is air viscosity. This is density. And this is bulk modulus. Now let me also write the dimensions. So force is mass into acceleration, mlt to the power minus 2. Then you have some constant of proportionality. Then you have length to the power a. Then velocity is length per unit time to the power b. Then you have air viscosity, which is mass per unit length per unit time to the power c. Then you have density, which is mass length to the power mass per length cube to the power d. And you have the bulk modulus, which has dimension of mass mass length inverse t inverse t square to the power e. So this is the dimensions. So according to Raleigh's method, I can now do, let's say, let me do m first. Then m is 1 equal to c plus d plus e. Then I have L. So L is 1 equal to A plus B minus C minus 3D minus E. Okay. And then T is minus 2 equal to minus B minus C minus 2 E. Fine. And from this, so as you can see, we have 3 equations and 5 variables. So certainly we cannot get unique values for all of them. What we can do is we can write some of the letters in terms of the others. So we have 5, so we need, so let's see. So C and D appear in all the equations. So they are a more suitable choice to choose as the variables in which we will express the other variables. So now I want to express A, B, and D in terms of C and E, because C and E are occurring in all 3 equations and it will be easier for me to solve them. So from the first equation, I have D is equal to 1 minus C minus E. Then from the second equation, okay, we'll come back to that one because there I have A, B, and D. From the third equation, I can write B in terms of C and E. So B is equal to 2 minus C minus 2E. And putting B and D in the second equation, I can get A is equal to 1 minus B plus C plus E plus 3D. So that is basically A is equal to 1 minus 2 plus 3. So 1 minus 2 plus 3 is 2. Then C plus C, 2C minus 3C. Is that right? So plus C, 2C, 2C minus 3C. Did I do it correctly? 2C minus 3C is minus C. And E is plus 2E plus 3E minus 3E. So that's 0. Okay. So now I have expressed A, B, and D in terms of C and E. Plus 2C plus C. Okay. So then I can write R as A L to the power A, which is L to the power 2 minus C, then V to the power B, which is V to the power 2 minus C minus 2E, then mu to the power C, and rho to the power 1 minus C minus E, and kappa to the power E. Okay. So this is it. So that's as far as we can go. We cannot figure out C and E. So basically, we have not found the function. Okay. And you can also see that if your variables become, as soon as they are more than 3 actually, you would not get a definite functional form for your equation with Raleigh's method. And it gets worse the more the number of variables. So you can actually try it for up to 4 variables, hoping that your equations decouple so that you're still able to obtain numerical values for your powers. But that is subject to it's on a case-by-case basis. So if you have up to 3 variables, you can always use the Raleigh's method. If you have more than 3, then maybe 4 or 5 you can try. In some cases it might work out, but it's not generally applicable. So there is now another method called the Buckingham Spy Method. So it's not that this gives you a way of doing finding the exact function through dimensional analysis. This is not this super method, but it helps you to organize your analysis a little bit more. So I believe Buckingham Spy Method was developed in fluid mechanics, but it has a more general, the principle is quite general, but the terms are sort of related to fluid mechanics. And you will see the most applications in fluid mechanics. So what is Buckingham Spy Method? So Buckingham Spy Theorem, something called the Pi Theorem. So if you have n total variables in your problem, including the quantity that you want to evaluate. So in my last example, n includes R, for example. So I have 6 variables in my earlier problem. Then, and a subset of them are defined as fundamental variables. And the remaining n minus 1 variables are grouped together to give the dimensionless variables, which are called the pi terms. So we will modify the n minus m number of variables and reorganize them into n minus m number of dimensionless variables. And these dimensionless variables are called the pi terms. So let's tackle the earlier problem with the Pi theorem. So I have R, L, V, mu, rho, and kappa. Okay. Then, how do we define fundamental variables? So which ones are fundamental? So according to the Buckingham Spy Theorem, in order for the variables to be fundamental, they must either be a geometric variable, so things like length, area, etc., or they have to be a flow variable, so things like velocity. And the third category is that they can be fluid variables, which means they are variables related to the properties of a fluid. So as you can see, he was very focused on fluid mechanics. Actually, I struggled to find an example which did not involve a fluid. So I don't know if in other fields it's actually a common practice to use it. Okay. Anyway, so then according to the Pi theorem then, do I have any geometric variables in my variable list? Yes, I do. L. So L is a length. So that's a geometric one. Then a flow variable V. That's a fundamental one then. And do I have a fluid property here? So I have a fluid property which is the density of the fluid. So I can choose that one. Okay. So I choose 3 as fundamental variables. And the remaining 3, R, mu, and kappa, I will use to construct my pi term. So I will have 3 pi terms. So we had n equal to 6, m we have taken to be 3, and n minus m is then 3. So I will have 3 pi terms. Okay. Also, one more point of caution. So the so my output variable is never taken to be a fundamental variable. Okay. So whatever the output variable for your function is, it is never a part of the fundamental set. So let's see how to construct these dimensionless quantities now. So the rule is that, so like I said, we will have 3 pi terms, and every pi term will have the fundamental variables and one other variable. So I'll have L, V, rho in all of them. And they can be to different powers. So I'll put A1, B1, C1, A2, B2, C2, A3, B3, C3. And I will multiply them with the non-fundamental variables. So you have R in one case, mu in the other, and kappa in the last one. Okay. So 3 of them and 3 more variables, so that's fine. Okay. Now I will apply the principle of dimensional homogeneity to each of these equations. So the pi's are by construction dimensionless. So these are dimensionless. So how does that simplify things? So I have from the first one, so this is, how to put it, M0, L0, T0 equal to length to the power A1. This is length per unit time to the power B1. Then I have density, so mass length cube to the power C1, and R is a force, so that's mass into acceleration. So notice that we have not put a power on R, mu, and kappa. So from this So I'm doing pi 1 now. So from this, what are the relations that I get? I get 0 is equal to C1 plus 1. Okay. And I get 0 is equal to A1 plus B1 minus 3C1 plus 1. And 0 is equal to minus B1 minus, so I'm doing times. So minus B1 minus 2. Yeah, if I make a mistake, just point it out to me as soon as you see it, okay? So I have C1 equal to minus 1. I have B1 equal to minus 2. And A1 is equal to 1 plus 3C1 minus B1. So to 1 minus 3 plus 2. This is 0. So I've got my pi 1. Similarly, I will do pi 2. So what is pi 2? M0, L0, T0 is equal to L to the power A2, LT minus 1 to the power B2, ML minus 3 to the power C2. And I have mu. So the dimension of mu was ML inverse, T inverse. From here we will get 0 is equal to, so I'm doing m now. So m to the power 0, 0, and then I have C2 plus 1. And I have from L, I have A2 plus B2 minus 3C2 minus 1. And I have from T, I have minus B2 minus 1. So this tells me C2 is minus 1, B2 is minus 1, and A2 is equal to 1 plus 3C2 minus B2, which is 1 minus 3, 1 minus 3, minus B2 is a plus 1. So 2 minus 3 is minus 1.
Ma'am, I think value of A1 is not correct.
A1 is not correct. So from L, I have A1 plus B1 minus 3C1 plus 1 is equal to 0. So
Then A1 should be minus 1 plus 3C1.
Okay. Yeah. It should be minus 1. Sorry. Minus 4 plus 2. Right. So this is minus 4 plus 2, minus 2. So then this is pi 2. Then let's do pi 3. So pi 3 is again M0, L0, T0 equal to L to the power A3, LT inverse to the power B3, ML to the power minus 3C3 and then I have kappa. So the dimension of kappa is m L inverse t minus 2. What happened? M L inverse t minus 2. Now let's see. So I have from m0 is equal to c3 plus 1, and I have 0 is equal to a3 plus b3 minus 3c3, and I have 0 is equal to minus b3 minus 2. So from here I can write c3 equal to minus 1 and b3 equal to minus 2 and a3 equal to minus b3 plus 3c3, that is equal to 2 minus 3, which is minus 1. Okay, so I found out the powers of my fundamental variables in the pi terms. So then I can explicitly write my dimensionless pi terms. So pi 1 is then L to the power minus 2, V to the power minus 2, and rho to the power minus 1 into R. So that's basically R by where did that go? R by L square V square rho, right? Then I have pi 2, which is now minus 1. So L to the power minus 1. So all of them are minus 1. So that's mu by L rho. And then I have pi 3, which is now kappa by L V square rho. So I've constructed the three-dimensionless variables. Fine. So once I had R as a function of L, V, mu, rho, and kappa. And now I have L, V, rho as my fundamental variables, and I have three other dependent variables or dimensionless variables. Okay. So I can reorganize them, all my variables, to a function of just the pi variables. Okay. So I have reduced now the number of variables. So I've made some composite variables using my using a subset of variables which I have called fundamental, and I've made some dimensionless quantities. And once I have made dimensionless quantities, I know that my I know that this equation will have like 0 dimensions, or m0, l0, t0 on the left hand side. So I can choose the right hand side to be 0 as well, and I can write my original function Okay, so this is of course a different function. So let me just clarify that. So I can write the original function that I wanted to find as a simpler function of three-dimensionless variables. And if you do an actual example, you will see that sometimes you can identify some of these pi variables as some known constants. So in fluid mechanics, something that occurs very often in various models is that one of these pi variables turn out to be things like the Reynolds number. Okay, and you immediately see that relation, and you know it's a constant. It's a dimensionless constant, and then it gives you some insight into your system. The fact that your resistive force, for example, if one of them turned out to be the Reynolds number, then it would mean that the resistive force depends on the Reynolds number of the fluid. So that could be an important insight. So the Buckingham Spy method does not tell you the functional form, unlike the Rayleigh's method when you can use it. But it simplifies your expression and can allow you to identify certain constants, and it sort of groups together the properties of the different components of your problem. So most commonly you will see that one of the pi terms becomes entirely a fluid property. Another pi term becomes some constant associated with the body that's moving or something like this. So the Buckingham Spy method, you don't know beforehand what you will get out of it. But it's a good exercise to do it because often it gives you some important insight. Okay. So this was about dimensional analysis. These are the two basic methods. There are more involved problems where you can use a combination of Buckingham Spy method and the Rayleigh's theorem, and you can do all this. But the other thing that I should point out, especially for those who will do quantum mechanics or atomic and molecular science, in those cases, it's a bit tricky to do any form of dimensional analysis. For one thing, usually to simplify expressions, the constants are done away with. Okay? And you just call them atomic units. But things like constants with dimensions, they are assumed to be one or just removed, okay? And they don't appear in your equation. So a quantum mechanical equation appears to be contradicting the dimensional theorem, but that's not the case. If you actually wrote everything in SI units, for example, you will be burdened with a lot of constants, but it will match. But in most cases, you just don't write them. Okay, so be aware of that. In classical mechanics, this is not such a common practice. Okay. At most, they would, club together constants and write some new constant. Okay. But you at least know that there is a constant or a constant square or two constants in the denominator or something. You would know that. But in quantum mechanics, they just disappear. And no one ever mentions them. When you will, of course, have to be careful of this is when you write a code and you want to report an actual measurable quantity. Okay? Then you will have to make sure that you know what units you are working in, the unit in which you've expressed your bond length. If you have for example, a constant like 1 by 4 pi epsilon 0, if it's there, or if it's in CGS units, it's not there. So when you write a code, you will become very aware of the fact that these constants are missing from the equations that are presented in books. Okay. But you should be careful there. So this is it. So we finished our course. If you have any questions, you can ask me. We still have 5 minutes. And we also have, of course, Friday's class if you have any doubts. But this is the end of the syllabus.
Ma'am, can you please upload these things in VLearn?
Yeah, so up to last class I have uploaded. I will update it with today's lecture as well. So, okay, so if you don't have any questions, you can stop the recording, and I will also then